Okay, so with this, we are doing a hypothesis test. Hopefully you guys have all had time to read through this. And we've got the office manager here believing that employees arriving late is greater than the claimed 7% rate. We want to see if this is likely to be true or not based on a hypothesis test. So the hypothesis, I'll write it up at the top, is going to be that no, the true proportion really is at 0.07. The alternative is going to be, we think that it's actually greater than 0.07. And so we want to test that. So we can assume here that the conditions for inference are met because all of the answers here assume that we're finding a p-value. So it's multiple choice. We can kind of skip over some of the formalities. All right, so what we want to do, of course, is come up with our test statistic, which in this case is going to be, well, in every case, the test statistic is your stat minus the parameter divided by the standard error. All right, and in our case, it's going to be a z stat, and it's going to be, our statistic is, well, we need to find out what that is. It's 23 out of 200, so our p hat is going to be 23 divided by 200, which is 0.115. Okay, so we're going to start with our stat 0.115 minus, now that our parameter is really, actually, I don't want to put the numbers in yet. I want to do it a little differently. So it's going to be p hat minus p sub naught, which is our assumed population proportion, divided by the standard error of p sub naught times 1 minus p sub naught divided by n. And now I'm going to plug the numbers in. So that's 0.115 minus our p sub naught is this assumed one right here. So that's 0.07. Maybe it's a good idea to actually write that out somewhere. P sub naught equals 0.07, so there's no confusion. Now we're going to divide that by the square root of 0.07. Notice I'm using p sub naught times 0.93 divided by, this is a sample size of 200. And now we can go through and do that calculation to get our z statistic. So I'll just calculate the numerator and denominator separately for now. Okay, and now when I do that division, it'll be 0.04 divided by my previous answer to get me, oh, 0.045, I'm sorry. I knew something was different. All right, sorry about that. I got 2.494. Okay, so that's my z statistic. I still can't answer this question yet until I do the last step, which is figure out what my p-value is going to be. Now remember, what we are doing is we are assuming we have this distribution right here with the mean of this sitting at the 0.07. That's our presumed population mean. Now we got 0.115, which is going to live right up here, 0.115, because our standard deviation right here, it's a standard deviation, is 0.018. So we need to move over only that far. And this results in a z statistic of 2.494. So that's kind of the whole visualization. We want to find the area of getting that value or more extreme. So I want to do a normal CDF calculation. And I won't plug in the parameters for that. But anyways, I'll do the normal CDF calculation. Because it's a positive test statistic, I want to get the value with that as the lower bound going up toward positive infinity. Okay, so now in the calculator, normal CDF Lower bound is 2.494, upper bound is infinity. And I get 0.0063. So that means there's only a just over a 6 in 1,000 chance that this is going to happen by random chance if the true population is proportion is 0.07. So this, because it's very, very unlikely to happen, our p-value is low, then we are able to reject the null hypothesis. And so we would say, is this strong evidence against that 0.07 claim? Yes, it is, because the p-value is so low, 0.0062. I know it says we're off by 1/10,000, so some rounding error happened. Okay, not a big deal with that. Hopefully that all made sense. You were able to follow along, and maybe you were even thinking through that full process before we got to it. Okay. Okay, so we are going to, the class is going to be set up a little differently. We're not going to be spending much time in this presentation. I have a different worksheet pulled up for us to kind of be going through. The worksheet is on the Canvas page, so later I encourage you to go and look at that, and I might even post the answer key for it. In fact, I will, in fact. But we're going to start by kind of looking at sampling distributions, and I want us to remember a few things about sampling distributions. We have some kind of a population that exists out there, all right? Depending on our scenario, there's a true population, and we don't have access to that knowledge, generally speaking. So we create sampling distributions, or the sampling distribution helps us interpret the sample data that we can pull from the population. So if I pull a sample of a certain size, so N of 50, I get a sample size of 50, then the sampling distribution will be approximately normal in a lot of cases. Even if it comes from a skewed population, then the sampling distribution itself, so this would be a sampling distribution maybe for means. And what I can do is I can compare the sample result that I got. So maybe I got an X bar that falls right here. I can compare that to where I would expect my X bar to land if this is the true population mean. Okay, now this is all hopefully good reminders, and you're like, okay, yeah, this is making sense. I know that a sample of size 50 won't stray too far from the mean, but if I went to the population and here is the mean, an individual could be way down here, way up here, but an average of 50 people from this population is going to be approximately normal. Okay, now it's important to figure out the direction we're going with this, and that we're not talking about one sample starting with today. And hopefully you did read chapter 22. We're going to be looking at a difference in proportions. So I'm not just looking at, oh, here's the proportions that exist or whatever in our population. Well, that proportions are a little different. But anyways, we're going to be looking at a sampling distribution for a difference in proportions, but it's still going to be, maybe we can interpret it a little differently now. So when I have two proportions, so I'll just say proportion 1 and proportion 2, if I subtract them, if there's no difference between these two proportions, then the difference between those is just going to be 0. But if proportion 1 is greater than proportion 2, then whenever I do the same calculation, then I'm going to get a positive number because proportion 1 is bigger. Now on the flip side, if proportion 2 is greater than proportion 1, when I do this calculation, I'm going to get a negative number. So this is going to be important to recognize that these numbers that we end up with, and they're all going to be, around 0.0 something, positive or negative, 0.0 something. These are representing the difference between two proportions, not an actual proportion itself. And we're going to create a distribution, which is going to center, typically, I'll change this to proportions now. It's going it's going to center typically close to 0. Not always. And our assumption is always going to be that it's 0. I'll tell you that. But the true sample proportion difference might fall like right here. Maybe you get a difference that's positive where your first proportion is bigger than your second one. And you get another one where, oh my gosh, you ended up way down here somehow. And your second proportion is way bigger than your first one. So just as kind of a conceptual setting up where we're talking about today. So we're going to talk about the sampling distributions first, and then we're going to jump into creating a confidence interval for that. All right, once we understand the idea that we're creating a sampling distribution and we're going to figure out what our standard deviation of this is, we're going to figure out how to find the mean of it. We're going to figure out just some things related to it, and we're going to use that information to create confidence intervals. And all this information, when we're done with it, is in the AP formula sheet. But we're not going to spend a lot of time on this page. I'm going to jump away from this in a minute. And let's see, do I want to do this first? Oh yeah, I want to do this before we jump into our activity. So I wanted to review a couple of things going back to random variables. Remember, your random variable, always a capital letter like X or Y or whatever else. These had certain rules associated with them. And this is while we were going through getting into like our binomial and geometric probabilities. And the key thing to remember is that the average, and here it's means, okay, but well, really, and it'll still be means for us, it's the average proportion, which if that sounds weird, but anyways, the mean of X minus Y is just going to be the mean of X minus the mean of Y. And that's going to come into play in a little bit when we look at our the average of our difference of proportions. Okay, so this is going to look familiar. We're going to change this. So I'll just put like a star beside this because it's going to look familiar in a little bit when we come across this. But really what I wanted to focus on is this right here. Remember that when we are finding the standard deviation of combined random variables, we always needed to add the variances. Okay, so the key takeaway here is add variances. Okay, and of course to do that, you take the square root of your random variable and you just square it. And then you take the standard deviation of your, did I say square root earlier? Sorry, I don't know what I said, but you take the standard deviation of your random variable and you square it. And then you can take the square root of all of that at the end. And that could keep going if you had more, like a third random variable Z. That should be a Z right there. Now, we aren't going to worry about having more than 2, but, you know, if it was a random variable, it could keep going. Okay, so I might come back to this later. I might not. But now let's watch this video. This is going to set up our activity that we're going to start with. And I know it'll be choppy, but you'll be able to hear it well enough. And that'll be good enough.
If anybody yawns in this room, I'm gonna catch it. First, the control. The group's left in the empty room for 10 minutes. Nothing to read, no talking aloud. Next, the lucky volunteers get to read some tax law. People, we have our first yawn. Now, will it travel round the room like a Mexican wave? The first 2 tests are inconclusive. So for test number 3, Scotty tries to infect the subjects with the yawning bug. But they appear to be totally immune. Unlike Carrie. am at a local flea market where the Mythbusters hope to get a bigger sample of test cases. This time, they are testing one variable only, the seated yawn. Carrie will yawn at 2 of every 3 subjects as she ushers them into their cubicle. And after the drought, a flood of yawning is unleashed. The Mythbusters suddenly have the Midas touch.
The results are in, and when the people we tested got no seed yawn, no stimulus, they yawned 25% of the time. When they got stimulus, they yawned 29% of the time. I'd say it's confirmed.
There's little doubt it does seem to be contagious. I bet the audience at home right now is probably yawning.
Okay, so that kind of sets the stage. We're looking at a situation where the Mythbusters are testing to see if yawning is contagious. And now we're going to move over to, is this the right one? Wait. No, sorry, I'm trying to find, okay, right here. No, wait, yes, sorry, it's not showing up on my screen correctly. There it is, I apologize. I'm gonna scroll back up here, and now we're just gonna be going through this. Is yawning contagious? So the first thing, this is just a good review of setting up and remembering experimental design, is what is the outline of this experiment? Okay, so first of all, we randomly assigned 50 subjects. All right, so there was some random assignment. Okay, random assignment, and we had, it turns out you don't have the numbers, so I'll just go ahead and give them to you. There were in 2 groups, so group 1 and group 2. And there were 34 that ended up in group 1 and 16 that ended up in group 2. And it was 34 who were given the yawn seed. So I'll just put yawn right here. And then I'll put no yawn. All right, and then at the end, we are now going to compare the results. All right, so if you think back to chapter 13 when we were doing experimental design, this should look somewhat familiar to you. But what we never did was move to this stage of it, comparing the results. Of course, we couldn't do it at the time because we need these methods that we're going to be learning. Okay, now I will say this at the beginning, so make sure you're hearing this. This could very well be confusing as we go through, because we're going to be looking at it at a conceptual level and then just straight up doing the calculations. You might get lost in this. Hopefully, you're prepared to ask questions and slow me down to get some help. But the best thing that you can plan on doing tonight, if you're confused at the end of class, is to read that chapter. If you haven't done it yet, you need to make sure you're reading the chapters, but then being prepared to ask questions, of course, is another great thing to do. Okay, so let's look at the actual results. And of course, you can see it's a 2-way table. And the key things to focus on right now is that they gave the yawn seed to 34 people. And then they noticed that 14 people, so I'm looking at the marginal totals. So were they given a yawn seed? Yes, 34 times. That's where that comes from. Did they actually yawn? Yes, that happened 14 times. And what we're going to do is we're going to figure out, could this distribution that we got, 10 yawns to 24 no yawns, 4 yawns to 12 no yawns, could that distribution have happened by random chance? So at the beginning, understand, we're going to figure out, is this a result of random chance, or is this a sign that something is really going on with yawning? Okay. So we're going to call P1 the true proportion of people who, when given the yawn seed, will yawn. So let me erase all this. We're looking at a conditional probability for P1. When you're given the Jan seed, so Jan seed yes, what is the proportion of those people who will Jan? We don't have that number. We're going to be looking for it. But we do know that 10 out of 34 people Jan'd in this condition. So 10 divided by 34 is, I'm going to round it off to 0.29 because that's what the Mythbusters did. Okay, now we want to see the proportion of people who given no Jan seed will Jan. So now this is kind of the control, if you will. So now we had 4 out of 16, which is 0.25. And now we want to do the difference in proportions. So this, you want to kind of decide at the beginning what your P1 and what your P2 is going to be. And it doesn't really matter because you can interpret the results either way. We're going to be testing to see, eventually we're going to be testing to see, is P1 greater than P2 or is P2 greater than P1? And you can test it no matter what. No matter which one you call P1 or P2. That doesn't change your ability to do it. But you will kind of interpret it different ways. So anyways, P1 minus P2 is going to be 0.29 minus 0.25, which is 0.04. Okay, so the next question, I'm not going to write anything down. I just want to ask you guys. Seeing that those who were given the Jan seed Jan'd at a 29% rate, and those who were not given the Jan seed Jan'd at a 25% rate, do we have some evidence that yawning is contagious? Is there any justification coming from the data that more people will yawn when someone else yawns? This might be a quiet day. Maybe you guys don't know how to talk.
I say maybe.
Okay.
Like a yes, but also a no, because if there was no probability, then I feel like we would have not gone 0.01, 0.04.
Okay. So if I understand correctly, you're saying the 0.04 shows that there's a difference, but is it that big of a difference? We're not sure about that. Is that kind of where you're heading?
Yeah.
Okay. Yeah, I think that's fair. Now, the next question, you can't quite see it on the screen, is would you agree that in the video they said, the Mythbusters were like, oh yeah, I think we've confirmed this myth. But would you agree, well, this is where that 0.04 is like, well, that's not a big difference. Is that something that could have just happened by random chance? Or is that because there was a Jan seed and it caused that value to be higher? And now we're going to see if it's statistically likely. Well, actually, we're not going to be getting that far with this one, but we will, to a degree, do that. Okay. So I'm going to take the answer just given as our baseline right here. That do you agree that that data is that yawning is contagious? We're going to put maybe, or maybe not, because that's not a big difference. And in fifth hour, there was a little discussion that happened, like what some people were saying, like it would be more convincing if these changes happened. Like if there was a bigger difference, if the difference was, 25% of people yawned just in general, and then like 50% of people yawned when they were given a seed, then that would be somewhat convincing to us. But also even that 0.04 that we got right here would be a lot more convincing if our sample size was not 50, but was instead like maybe 1,000. So if 1,000 people did that, you got a 0.04, well, that would be some pretty convincing evidence too. So the reason for that is all in the calculation. Okay. Okay, so here's what we want to do to get started. We're going to do a simulation of this in a second, but you guys are getting off a little easy on this. You're not going to have to do the simulation. We're just going to walk through the simulation and then automate it a little bit. So the null hypothesis right here is that there is no difference, that whether someone yawns or doesn't, people are going to yawn at the same rate. I keep talking about yawn, it just makes me want to yawn. And I'm sure some of you at home are doing that. Go for it. All right, so our null hypothesis is that whether you're given the yawn seed or not will make no difference. So the difference between those proportions, that's a minus sign, not an equal, is 0. No difference. Okay, so we might say something to the effect of the treatment doesn't affect the outcome. Okay. So if we were going to do a simulation of this, because the purpose of the simulation is to say, how often do we get a result of 0.04 or greater just by random chance? And we want to figure that out. Of course, we're going to learn the formulas for a sampling distribution so that we don't have to do a simulation for it. But for right now, we just want to kind of practice with simulation and figure out how would we do this. So we know that when they did their test, the Mythbusters, 34 of them got, so I'm not talking about the proportion right here, but the number, this group, I'll put n sub 1 because it's for proportion 1. The number who got this was 34 people. And the number who were in this group was 16 people. So we know that that's kind of the distribution of who got the yawn seed versus who didn't. Secondly, I'm not going to scroll back up to the table, but the results were that 14 people yawned overall, just total, versus 36 who did not yawn. So right now it doesn't matter how it was distributed. What we want to figure out, yawn, okay, it's hard to spell yawn in cursive. That says yawn. Let's pretend it does. Okay, so we've got overall 14 people yawned, 36 didn't yawn, and now the way it was actually split up was it was 10 and 4. Now, is this an unusual arrangement that it ended up that way? We're going to do an experiment to randomize this. So here's what I want to do. I'm going to pretend I've got 50 people in a random number generator. So my random number generator goes from 1 to 50. And if it's 1 to 14, that represents it's one of these people who yawned. So this is a yawn. If it is 15 to 50, then it's going to be no yawn. All right, and that's going to represent one of these people. So the actual distribution of those people between our control group and the seed group, that is going to be our test. Is it unusual to get 4? Or would you expect to see a different amount, knowing that 14 total people yawned? All right, so I hope this makes sense. I'm going to run through this once using a random number generator. You do not need to do this. So you can just kind of pay attention to the logic. I'm bringing up a random integer on the calculator. And I'm going to go 1 to 50. So that lets me pull any random number there. I don't want repeats. And what I'm going to do is I'm going to figure out of 16, because it's a smaller number, I'm going to do the 16 times how many people yawned out of 16. All right, so I'm going to, down here, I'll put Y or NY. So yawn or no yawn. Okay, and I'm gonna do this 16 times because these are gonna be the 16 people who did not get the yawn seed. And this is just randomly done. All right, so 23 is the first number. That means it's no yawn. Then it's 45. Then it's 19. Then it's 27. Then it's 32. If I say a repeat, hopefully I can catch it. 31 is a new one. 3, okay, there's a yawn. Up 3 again. 12. 28. I don't know if I said 28. Anyways. 9, there's a yawn. 45, I already got a 45. 12, I already got. 4, there's a new number. Okay, let's see, I've done this 5, 6, 7, 8, 9, 10, 11 times. So 5 more numbers. 41, 26, I think is new. 13, I don't remember if I got a 13. If I make a mistake on this, I apologize. There's 18, so just one more. Okay, that's a new number. Okay, so here's the breakdown. Out of 16 people who did not get the yawn seed, in this trial, 5 of them yawned. So that was 5 out of 16. And then that means that there were, knowing that 14 total people yawned, that means 9 of them out of 36 did not yawn, because there are 36 who, oh, yeah, 30, dang it. Sorry, it was the difference. Sorry, it's this 34, not 36. Okay, so if this makes sense, these two numbers should add up to 50, because that's my 2 different sample sizes that add up to 50. In the first sample, 5 out of 16 yawned, and that means for the ones who got the yawn seed, 9 out of 34. Now these numerators have to add up to 14, because that's how many total people yawned. All right, again, I hope this is making sense. So now my proportions for this one, well, what's 5 divided by 16? That's 0.3125. And then what is 9 divided by 34? That's 0.2647. So these are my P1 and P2. The difference here is actually going to be negative. So if I do subtraction here, 0.2647 minus 0.3125, I'm actually going to end up with a negative. I'm going to write it somewhere else. I didn't give myself, I'll just erase all this. Again, I'm only doing this simulation once, and I'm going to let technology take over from here. So this is going to be negative 0.0478. Now imagine I could do this over and over and over again, and I get some specific outcomes. Okay, and maybe I'll get this negative 0.0478. There's only so many ways this can come out because it's discrete. So there's only so many different outcomes we can get. Okay, so let me transfer us over to this, and I'm going to pull up this app right here, this applet. All right, so notice that yawn, actually it wasn't 11 and 3. This was 10 and 4, and that should be 24 and 12. Oops, 12. Okay, so that is kind of the table that we're going to be working with. All right, so this is the outcomes that we got. So knowing this, that same simulation that I just did, and you can do it with cards also, I'm going to do this multiple times. So I did it the one time I got a negative 0.04 or something. So that would have ended up, I don't know, somewhere about right here. I might have added a dot somewhere in that range because it was in the negative 0.05, basically. Okay, now I'm going to do this 10 at a time. I'm going to do 10 more of those simulations. Let me get rid of that dot. Okay, it's working, sorry. Okay, now you can see we got this going on. Now at first, I mean, it's starting to look more and more normal. I'm gonna do this. I'm gonna get 200 results. There it is. Our 200 results right here. This is 200 trials or 200 simulations run. And notice that this one dot right here represents one outcome. So this is one time going through and figuring out a p hat sub 1, a p hat sub 2, and getting the difference between them. And it looks like on average, so whatever that mean happens to be, but on average now, this distribution has this layout. In fact, maybe I want to keep those numbers in mind. That 0.006, I don't think is gonna, we could assume it's basically 0.00. Okay, and the standard deviation here, because we're gonna come back to that one later, is 0.133. Okay, so this is not a true sampling distribution, but notice that it is approaching a sampling distribution. This is not every possible sample. Remember, you're going to have millions and millions and millions of possible samples that could be drawn from this population. We only did 200 of them. And we're ending up with this. So now what I want to do is I want to pretend, what if I could come up with a true sampling distribution for this difference? Then what would my mean and standard deviation be? Well, the mean is just going to be the true difference between population 1 and population 2, or population proportion 1 and population proportion 2. So I'm going to say that it's going to be approximately 0. My mean here of the difference is going to be approximately, I'll put the wiggly equals approximately 0. Okay. Okay, so that's all well and good. We'll just pretend that it kind of hovers somewhere around 0. All right, now we are going to do the standard deviation of this. And remember what we talked about before this was when you have a difference, and we're going to treat these proportions as though they're random variables. So that's going to be the square root of the variances. Okay, so now let's kind of go, but what is the variance of one sample proportion? All right, so the standard deviation of a sample proportion is going to be p hat times 1 minus p hat divided by n. And that means the variance of this is just going to be each side squared. So just to simplify this a little bit, if I square the square root, then it goes away. Oops, okay, so that p should still be there. All right, so there we are. That's the variance. So I want to do that, but now I've got the variance for P1 and the variance for P2. Even though I'm subtracting these two, remember we always add variances. So it's going to be P hat for 1 minus P hat, that's it for 1 still, divided by the sample size for 1, plus P hat for 2 times 1 minus P hat for 2, all divided by the sample size for 2. We will work with this more today. So if it's not making 100% sense, like how we are going to plug these numbers in, we'll see that later. Okay, so this is kind of a big takeaway from this lesson. Your standard deviation, 0.133, should look, is found by using this calculation. In fact, now I wanted to plug some numbers in. Our P1 was 0.29. Our P hat for 2 was 0.32. 0.25. That was what we got from the samples. That's equals right here. So I want to plug these in. I know my sample size for this one was 34. My sample size for this one was 16. So let's figure out what the standard deviation should be for the sampling distribution. So I'm going to do 0.29 times 0.71 divided by 34 plus 0.25 times 0.75 divided by 16, and then take the square root of all of that. And sure enough, when I do that calculation, I get 0.13332, so on. Were you guys getting the same numbers if you plug that in? So now we can see that this is not, now we just kept doing iteration after iteration of this simulation, and we kind of, they call this bootstrapping, and then we came up with our mean and our standard deviation, right? But it is not, what's the word I'm looking for? But it does just come from a simple calculation. I would call this a simple calculation right here. All right. So now I think we can kind of wrap this up, and I wanted to go back to this real quick. Okay. So there we go. You can see it right here, that the standard deviation here is just going to be your first proportion variance plus your second proportion variance. That's the formula that we came up with. And you just take the square root of it all. The mean is just going to be the true population proportion minus this, the second population proportion. And this is another thing that we didn't talk about, but it's important to cover here. In order to create a true normal distribution, we need to make sure we meet the large counts condition, but we have to check it for both samples. So it'd have to be N1 times P1 greater than 10, and then the same over here. And then you do the same for your second. So we'll run through this check in a little bit. And both of them also have to pass the 10% condition. Okay. So here's that kind of summarized. You can see the your proportions right here. Both samples are random. Both meet the 10% condition. And for confidence intervals, you need to meet this condition. Okay. All well and good, I hope. I will pause right here in case there are any questions. And I wanted to show you real quick on the AP formula sheet. Look right here. You've got your sampling distribution formula for the standard deviation. Here's the mean. And this is what we're going to use when we get to our test statistic. Though, I mean, we're also using it for our confidence intervals. The only difference is that it's p hat. This part right here, we're not talking about today. So we're not going to worry about combined proportions. But notice that this is when we're using two populations. So this would be a 2-sample test or a 2-sample interval. And we'll talk about that in a second. So this would be, we've learned everything just for one population here, one population here. Now we're going to be looking at how to do it for 2. So now let's create a confidence interval. And I will share this. Okay, I might make this small enough that I can just write on this one screen. Okay, so we're going to kind of jump ahead. What we did, we just figured out that if we had a sampling distribution that was centered around the difference between two proportions, the difference between them, then we want to figure out the sample difference that we got. Is that sample difference far enough away for it to be considered extreme? Actually, we're not really testing that right now. What we're going to be doing is, sorry, I was jumping ahead to doing some test statistics. What we're going to be doing is we're going to be figuring out the confidence interval that would exist around this value right here. So does this confidence interval include how far would we stretch for this difference? Okay, so we are looking at how many people use Twitter regularly. So a recent random sample of 200 US females revealed that 110 use Twitter regularly. A separate random sample of 150 males revealed that 60 use Twitter regularly. We're going to construct a 95% confidence interval for the true difference in proportions who use Twitter regularly. And we're going to use females minus males. So it's going to be, this will be P1 and this will be P2. And we're going to be subtracting between those. So now we know that whenever we're looking at the 200 US females, that's in sub 1. And P hat sub 1 is going to be 110 divided by 200, which is 0.55. All right, so P2 is going to be right here. So for men, that's going to be N sub 2, 60 out of 150. So P hat sub 2 is going to be 60 out of 150, which is 0.4. Okay, so we're not doing the actual calculations yet, but we set up a couple things. We know what P hat 1 and P hat sub 2 and N1 and N2 are. The parameter that we're checking, we want to see if this difference, what this difference really is. We want to find the true P1 minus P2, which is going to be the true difference between them. True difference in proportions, and that'll be females minus males. Okay, our statistic here, remember your parameter is the population. So the statistic is going to be this, P hat 1 minus P hat 2. And we happen to already know those numbers. We can do the calculation because P hat sub 1 is 0.55. And P hat sub 2 is 0.4. So the difference here is going to be 0.15. So let's remember 0.15 is the difference between these two sample proportions. Okay. And yeah, I'm just trying to think if there's anything else I wanted to say. We are setting up the confidence interval to estimate this. That's why it's an inference method. The confidence level is 95%. And remember that our confidence level, we end up with a critical value. All right. And the critical value comes from table B. This is one of those numbers you might have memorized. So in this case, the critical value is 1.96. So that represents, we're going to go out just under 2 standard deviations away, standard errors away from our point estimate, and that will represent 95% confidence. Okay, we want to identify the appropriate inference method. So we didn't say it before, but this is what we call the 2 sample Z interval. And that's good enough. You could also add Z interval for P1 minus P2, but that's unnecessary. Really, this name right here, 2 sample Z interval, is good. And it's 2 samples because we had a sample of females and a sample of males, and we're getting the difference. The conditions have to be met. First of all, it has to be random. Was it random? Well, it says here is a random sample of males or females and a random sample of males. So actually, I'll set it up this way. So I'll just put 2 check marks. It's good for one and it's good for the other. All right, we have to make sure it meets conditions in both cases. 10% condition. All right, 200 females is definitely less than all US females. And 150 males is definitely less than all US males. So we met it for both. And then is it normal? Which really means, is it meet the large counts? So I know this is still a point of confusion for some people, but we only use large counts if it's proportions. If it's means, we have to use the central limit theorem or an approximately normal population. We'll get to that later. We'll come back to it later. So remember, we have to check this for each. I have to do N1 times P hat 1. All we can do is check P hat. And then N1 times 1 minus P hat 1. And both of these have to be greater than or equal to 10. We have to do the same thing for N2 and then P hat 2. So we have to do this calculation a few times. It's a little bit more time consuming to make sure that both of them are greater than or equal to 10. If I did this 200 times 0.55, I'm going to get 110 again. So this is going to be met. And then the other would give me 90. I mean, I'm not going to do the math right now. You can figure out your 1 minus P hat and do that. So I will go ahead and say, just to save a little bit on time, all 4 of them are met. If you have questions on how to show that, you can ask me. We can go into more detail. But I'm going to assume you guys can find your how to check those conditions. All right, maybe I should just do one of this though, just to make sure it's really clear. N2 and P2 means I need to take the probability right here. It's going to be 0.4, and then N2 is right here. So it's going to be 150 times 0.4, which is going to give me my 60. And then if I do 150 times 0.6, which is 1 minus that, I'm going to get 90. All right. So I did kind of run through it a little bit. We met all conditions. We're ready to move forward. The general formula for a confidence interval is it's going to be stat plus or minus the test statistic. No, I'm sorry. I'm messing you up. Messing myself up. It's the critical value times the standard error. All right, and this is the formula from the formula sheet. So you want to kind of show that, say, hey, this is what I'm gonna do. This is my starting point. Now I want to customize it for this particular problem because my specific formula is that I'm looking at a difference in proportions. So P hat 1 minus P hat 2 is my stat. Plus or minus, and notice we already calculated that up here. All right, plus or minus, my critical value is going to be a Z star value. And the standard error, this comes from the formula sheet, but it's the one we already introduced, is going to be P hat sub 1 times 1 minus P hat sub 1 divided by N sub 1 plus P hat sub 2 times 1 minus P hat sub 2 divided by N sub 2. So that's my specific formula for this problem. It looks really complicated. So, hey, that's just, you can impress people. You can show them that you know how to use this formula. That'll impress them. All right, so the difference between it is 0.15. I already have that statistic, plus or minus. My critical value is actually 1.96. And I had that written up here. But that came from the table. You don't have to have it memorized. And now I get to plug these numbers in. This is going to be, let's see, P hat sub 1 is 0.55 times 0.45. So I'm just doing that math in my head real quick. Divided by the sample size of 200 plus 0.4, which is p hat sub 2, times 0.6, which is the complement of it, divided by 150. And I want to calculate the margin of error first. So it's going to be 0.15 plus or minus some margin of error. I'll pause there so you guys can do the math, but I wrote the answer that I got up on the screen. Once you get that, you can actually do the addition and subtraction from your point estimate to figure out the actual confidence interval. And you can round it to 3 decimal places or whatever you want. I'm just gonna put it right there. Okay, and that's the confidence interval I got. It's worth pointing out right now. Trying to pause in case you guys are finishing something up. Okay, it's worth pointing out that these are both positive numbers. Keep in mind, we're talking about a difference between two proportions, and you can easily have negative numbers, but our entire confidence interval is positive. So what does that mean as far as which one's bigger? What is likely to be bigger according to our confidence interval? The true proportion for females or the true proportion for males? So is this going to be P1 is greater than P2 or P1 is less than P2?
P1 is greater than P2?
Okay. That's going to be the conclusion that we come to, because in every case in our confidence interval right here, our P1 value is greater than the P2 value, and we ended up with a positive result. If anything in our confidence interval was a negative number, then that would have been a situation where P2 is greater than P1. But there is no outcome with a 95% confidence where P2 is greater than P1. Every one of them has P1 greater. And remember, this is related to the females and this is males. Okay, so we're going to write a conclusion for this, and there is a, hopefully you remember this, this template. We are 95% confident that the interval from 0.046 to 0.254 captures the true difference in proportions of females and males who use Twitter. Okay. And we could conclude this by saying there is convincing evidence that females use Twitter more than males. Now, I can only make that conclusion because my entire confidence interval was positive, just like we were talking about before. If it went negative to positive, I could not state what I just stated there. We could not be confident that females use it more than males because there's a possibility that males actually use it more. All right, hopefully that's clear. If you guys want to screenshot that before we move ahead, I'll pause for a second because we're about to lose all that writing. Okay, and moving forward, we are going to now go back to the presentation and we will look at the a practice problem. We'll summarize and then we'll do a practice problem and call it good for the day. If you still have questions, you can stick around after that, but let me get back to this right here. Okay, so when we left off, we were looking at the conditions for inference. We do need to meet those conditions. Confidence intervals, again, your generic formula, working your way down. I should add these came from the reference posters that are posted on the Canvas page. Some of you might have already downloaded these and have access to them, but if you don't ever look at those, you can see how helpful they are. They include some really quick references for like, okay, it's proportions, it's confidence intervals for a difference. Here's my formula that I use. Of course, you need to understand this conceptual part of it as well. So don't just get stuck on memorizing formulas or, focus only on that. Okay, and the conclusions we can use is if the confidence interval is positive to positive, like our example was, then P1 is greater than P2. If it's negative and negative, then P2 is greater than P1. So just keep in mind, if we had switched to like this, where it was males minus females in our example, there's nothing that said we couldn't do that. But if we had switched it to males minus females and males had been P1 and females had been P2, then we would have ended up with this kind of a confidence interval. And we would have said still that P2 is greater than P1, females were still greater. But if you end up with this kind of confidence interval, you cannot make any kind of decision. No convincing evidence. Okay. So let's look now. Hopefully this is all feeling like it's making sense. All right, let's just look at this example real quick and we're gonna call it good for the day. So we are going to basically, they split it up into a bunch of questions, but we're essentially gonna run through the full process. So I'll kind of ignore those questions. So in October 2000, the US Department of Commerce reported the results of a large-scale survey on high school graduation. Researchers contacted more than 25,000 Americans aged 24 years to see if they had finished high school. 84.9% of the 12,460 males and 88.1% of the 12,678 females indicated they had high school diplomas. So first of all, let's kind of start at the beginning. We want to show that I will call, in this case, males our, they'll be P hat 1. So this is a sample, so this will be P hat 1, and this will be N1. This right here will be P hat 2 and N2. So P1 minus P2 is what is the proportion, is the parameter that we're trying to estimate. And with this, we're going to say that the true difference in proportions of male and female graduation rate. I'll just put in male and female graduation. We're going to be using p hat sub 1 minus p hat sub 2 to estimate that, which is, all right, p hat sub 1 is going to be 0.849. I'm getting that straight from the problem right here. And then p hat sub 2 is going to be 0.881. Again, you can read that in the problem. And so I want to figure out what that is. So 0.849 minus 0.881 is negative 0.032. So there's my statistic. That's my point estimate. Okay. We're not saying that's the true difference. We're saying that that is our estimate from this sample. And we want to check the conditions and assumptions for inference. So I'm going to do it this way. I'm going to have P1 and P2. This will be male and female. Then we got random, 10%, and normal, which is our large counts. All right. So if I read the problem, it doesn't specifically say that this is random. I think it's a safe assumption that it was. So I'm going to go ahead and assume that we did. It doesn't say that there was anything fishy about how they collected the data. 10%, that's a lot of males and females, but it's still less than 10% of the US population of each gender. And now we get to normal condition. And just as a reminder, you have to do N1 times P1. Now it's P hat 1 and 1 minus P hat 1. And these both have to be greater than or equal to 10. And then do the same thing for N2 and P2. So these should all be P hat. Okay, now here's where I will get a little bit lazy. There's over 12,000 in this sample. I hope you guys understand that with 12,000 in your sample size, you are not going to run out of, you're going to have at least 10 failures and 10 successes. That's pretty obvious. So I'm going to go ahead and just say, yes, we met both these. I could be more thorough and actually do the calculations, but it really is going to be just not necessary. So I checked the assumptions. So now I'm going to be doing a 2 sample Z interval is how I would describe the test I'm about to do, or the process I'm about to do. Okay. All right, let's look at this. We want to look at, so we've got our statistic plus or minus the critical value times the standard error. Again, now we get to do our fun formula. P hat 1 minus P hat 2 plus or minus a Z star critical value times standard error is going to be the standard deviation, or sorry, this square root of all this. Okay. So there it is. And now what we want to do is do this calculation. We have all these numbers, we can plug it in. So let's go for it. The difference is negative 0.032 plus or minus. Our critical Z value for 95% is 1.96. This is going to be, so for P1, P hat 1 is going to be 0.849. And the complement to that is going to be 0.151 divided by, that's a big number, 12,460. Plus, it's going to be 0.881 times 0.119 is the complement divided by 1,200 or 12,678. Okay, I'm going to calculate the right side first. And I got 0.0084 for my margin of error. So I'll be almost 1% above and below that. And we had to set it up this way because we're combining the variances of each of our proportions. Okay, so now I can actually set up my confidence interval is going to be negative 0.032 minus 0.0084 gets me negative 0.0404. And then I'm going to add that margin of error to it, negative 0.032 plus 0.0084 gets me negative 0.0236. So it's important to remember what this means. If I think of a number line here, and I put 0 right here, I just created a confidence interval that says, I'll just put my point estimate right here, it doesn't matter. My point estimate has a margin of error around it. And that entire margin of error is negative, is left of 0. And this is the difference between male graduation rate and female graduation rate. So we are looking here at a situation where we can draw a conclusion. What conclusion can we draw? Which one's greater, P1 or P2?
P2?
P2 is greater because it's always negative when we're subtracting. So there it is. P2 is greater than P1. Okay, so now let's now come up with our conclusion. We are 95% confident that the interval from negative 0.0404 to negative 0.0236 captures the true difference in proportion of male and female high school graduation. So, of course, remember with the template, you're just providing that context. We're talking about male and female high school graduation. And then we can add a little bit here. We have convincing evidence that females graduate at a higher rate. Than males. Okay. And of course, you can phrase this different ways. This is just a good template that will always convey the right information, the right meaning. So there we go. Are there any questions on any part of this process we just went through?
So if the P1 hat and the P2 hat, if they're both negative, is that when it means that there's no convincing evidence? Not like the final where it's 0.040 and 0.0236, because those two are negatives.
It's the confidence interval. These two have to be negative. Because your proportions, your P hat and P hat 1 and P hat 2 are always going to be positive. But it's the difference between those two that, because if you subtract two numbers, you know, depending on the magnitude of each number, you could end up with a positive or a negative number, right? So if we end up with a negative number, then that means that our second proportion was bigger than the first one. And if that's true on both ends of our confidence interval, like it was here, then that means we're 95% confident that the true difference is going to be negative, which means P2 is bigger.
Oh, okay. Because I thought if there were two negatives in the confidence interval, then it was. But if one's greater, it doesn't matter.
It's if they're both the same sign. So this was a negative. I'll put it just, I don't have much room here. So this is a negative and a negative. So they're both the same sign. It's if you have two different numbers in the confidence interval, like let's say this had gone to positive 0.0236, then that captures 0. 0 is the break-even point where both of those proportions are equal. So, and then of course, positive numbers would mean proportion 1 is greater than proportion 2. So if this was a negative positive right here, then we could not make this, we'd have to scratch out this conclusion. Say, never mind. We would just say, we do not have convincing evidence that there's a, that males or females graduate, you know, more frequently.
Oh, okay. Okay, I get it now.
Okay. All right, any other questions? I'll just say this, if there are other questions that you just want to stick around to try and get some help with, that will work. If you are good to go, I was going to do a second example, but I won't. So read chapter 22, it's an exclamation point to say, make sure you're doing that because you might still be confused on things, but the book has all kinds of extra information that I don't cover. So that's always been a good idea to read your book, but make sure you're especially doing it if you're struggling with what we're talking about today. Here's your homework. I will say chapter 7 is, or problem 7 is more of a review of previous things, but then 9 through 13 are going to be pretty standard create confidence intervals, practice with what we're doing today. So make sure you're looking at 7 so that you can get some good practice of previous things. And with that, if you are feeling good about today and you're ready to move on to the weekend, have a wonderful day. I will see you on Monday. And if you still have questions, feel free to stick around.